Well, this next one is a story almost out of a science fiction novel. Researchers have discovered a supermassive black hole in a galaxy 55 million light years from Earth, and they have the pictures to prove it. The international team of astronomers say this is the first visual evidence of the black hole in the center of the M87 galaxy. And the image that made headlines across the world has a local tie. The UMass Amherst research team who worked on the project sat down with me to explain their role in the discovery and what this all means.
What we discovered is, what we made is the first image of a supermassive black hole. This is an object called M87, or Messier 87, which is in the center of an elliptical galaxy in the Virgo cluster, which is at a distance of 55 million light years away. It is a black hole which has a mass of 6.6 billion times the mass of our sun, packed in a volume of space about the size of our solar system. So we've known that there's probably an evidence for a black hole in this galaxy. There is such an evidence for a supermassive black hole in the center of our own galaxy. It's called Sagittarius star. And the black hole in the center of our own galaxy is only 4 million times the mass of our sun only. But this one is 2,000 times bigger, but also about 2,000 times further away. So the biggest thing about this first image is that this is the very first time an image has been made of the event horizon around a supermassive black hole.
Explain what the event horizon is. That's an important point.
Right. So black holes can range from essentially a few times the mass of our sun to billions the times of our sun. All of them share the same physics of it, in the sense that a black hole is an object that where gravity has gotten to be so intense that even light cannot escape. There is a region around the black hole called the event horizon. It's a diameter of order 5 times that of what's called the Schwarzschild radius. The Schwarzschild radius is a distance around a black hole that's just based only on its mass. Black holes came out of the theory of general relativity that Einstein came up with. In fact, it's kind of ironic, and it's also interesting, that 2019 is when we announced this discovery. And 1919, 100 years ago, was a seminal observation that proved that Einstein's theory from 1915, general relativity, was without a shadow of doubt proven by observing a solar eclipse, observing star bending around the gravitational bending of the sun. So 100 years later, we're releasing this first image of a supermassive black hole. And what's interesting about this is that it shows without a shadow of doubt that Einstein's theory of GR, general relativity, still holds. And even in this extraordinary mass scale, it still holds.
Can you explain a little bit more about Einstein's theory?
So Einstein's theory of general relativity made a fundamental leap in intuition. It's something completely different from the Newtonian concept of gravity. Isaac Newton, thought of gravity as being of two massive objects being attracted to each other. Einstein had this intuition that gravity tends to warp space-time. So a massive object tends to bend space-time around it. And that's what causes objects to fall into each other. The whole space-time is bent by massive objects. And general relativity goes on to expanding that idea. So in the case of the M87 black hole that we detected, because it has 6 billion solar masses in there, the space-time around that region is so heavily bent that light around it swirls, and even light is bent, and the whole space-time is curved, so that as you're standing at the event horizon, you can actually look at the back of your head, because the light from your eyes go forward and comes right back. The whole light and space-time behaves in odd ways because it's such a massive object there.
So Ron, you're smiling a little bit because you know that I'm thinking in my head, this is science fiction. This is so interesting and high-end. But tell me a little bit about the involvement that UMass had in this project.
Well, we built a radio receiver like the radio receiver in the dashboard of your car, only 1,000 times, 2,000 times higher in frequency and much quieter. You know, when you turn, in the old analog days, you could tune the knob on your radio receiver in between stations and hear nothing but static. Well, we're trying to build radio receivers with very little static in them and go to great lengths to accomplish that by cooling the detectors down near absolute zero of temperature, where everything gets quieter. At least the things we pick get quieter. And so there's packaging these receivers in vacuum vessels, because vacuum is great thermal insulation. And then you have to bolt them to a telescope and point them at the sky in just the right way and arrange for the signal coming out the back to go somewhere useful and build all the stuff for analyzing that signal in a useful way as well.
And so what you built was put on a telescope in Mexico, is that correct?
Yes.
And you worked with a team down there, but there were actually 8 telescopes that detected this?
There were 8 such telescopes. And the LMT, the Large Millimeter Wavelength Telescope in the country of Mexico, is one of those. It's a 50-meter diameter telescope, which is the world's largest millimeter wave telescope, bar none. And so that's one of the primary telescopes in this Event Horizon Telescope Array. There are 7 other telescopes scattered around the world.
Okay, and Alex, what was your involvement in the project?
So I did the observations. I went down to Mexico to participate in the campaign for 4 years. And I also helped out in the lab for our receiver development.
And how do you feel being part of this project, you know, with this news that has come out?
I feel incredibly lucky, and it's a great honor.
And so when we look at this, so there's 8 different telescopes that had been used to detect these images. How many years did it take you to get to this point?
So I can talk first about the LMT itself, and then we can talk about all these other telescopes and how they were synchronized together to behave like a whole Earth telescope. The LMT is a rather tough project. It's a 50-meter diameter telescope being built on top of a 15,000-foot extinct volcano in the country of Mexico. Mm-hmm. We build it on top of these high mountains because you want to be above the Earth's water vapor levels and oxygen levels to be very high, because those molecules in the atmosphere absorb radiation. So we want to be as high as possible. And this project, building a 50-meter diameter telescope, open-air telescope, sitting out in the sky, there's a lot of technological problems, the challenges we had to circumvent and solve. And it's been a long haul, 20 years of working on this. All of us have been, and many more engineers and scientists in UMass have been involved in this. And in the country of Mexico, it's been a lot of people's efforts that went into building this telescope. And so it's a great deal of, how shall I say, pride and joy to see these results come out from the LMT, because a lot of us have put in a lot of effort into this. And along the way, we built multiple receivers. Our lab has built receivers that have been put on the telescope for other projects, not just the Event Horizon Telescope project, but for detecting the first galaxies that formed after the Big Bang, to looking at molecular gas in between stars in our own galaxy to nearby galaxies. So that's the LMT, and it's been a long project. But then there are 7 other telescopes. This experiment that relied on getting 8 telescopes to work together relies on having extraordinarily accurate timing, that we record the data with precision time. And the timing has to be in the order of nanoseconds. That's 1/1000th of a second. Accurate timing needs to be put in there. So we use atomic clocks derived from hydrogen masers. These are $250,000 to $500,000 pieces of equipment in each telescope. We use GPS signals to synchronize our timing together. Extraordinarily high frequency resolution is needed, and accuracy is needed. And there's a huge checklist of items that needs to be done at each telescope. And all the telescopes incorporated these various pieces of equipment to synchronize the data taking together.
Now, Ron, this has to be extremely exciting for everybody up at UMass as well, you know, just to be part of this project.
Absolutely. We're a small part of the team that put together all the bits and made the measurement. from my perspective as an engineer doing the details of some of the construction, receiver construction work, working for these astronomers is a bit of a lottery ticket, that something I work on might get used to discover something really important. And this feels like that, one of those. This is very exciting.